Morning, seniors. You guys awake yet? I hope so. No doubt you figured out that I'm not here today. So what I've decided to do to get through with the more not as much fun stuff, I decided to make a screencast for you today to get through some of the notes and things like that for some of our topics here in class. Here we go. This is just Coke, by the way. All right, so continental margins and ocean basins. Fill in your notes, please, as we go along. If I'm going too fast, just hit pause. It's a beautiful thing about screencasts. So, continental margins. There's three main divisions. The shelf, the continental shelf, the slope, and the rise. Shelf, slope, rise. Okay, three main divisions. We're going to talk about each one of them. So the continental shelf is the submerged part of the continent. On the left side here you can see a diagram of each part of the continental margins. The shelf slopes gently toward the ocean basin and is composed of continental crust. The shelf ends at the shelf break, which is the boundary between the shelf and a steeper slope. In this case, the continental slope. So it extends from the shelf break to the rise. The boundary between the continental and oceanic crust is steeply sloping compared to the shelf. So you can see in the shelf over on the diagram, there's not much of an incline to it. However, the slope, there's a much more steeper incline. Submarine canyons are major features. We're going to be talking about those next. But first, the last bit is the continental rise. So it's at the base of the continental slope. So you can see there on that diagram, you have the relatively shallow shelf, and then the slope, and then the continental rise as it slopes down. Okay, it's at the base of the continental slope. It's a slope angle decrease, and it's caused by the accumulation of sediment over time from basically the continental shelf sliding down the slope. Submarine canyons. What they are, the origin of them basically is river erosion over time and turbidity currents. And we're going to have a lab later this week on turbidity. So turbidity currents are the downslope movement of dense mixtures of clay, silt, sand, and water. Basically all mixed together, working underwater, kind of like when you take your hand and you put it underwater, and you put it over some like mud or something, or your feet, and you just move it around. You have a whole bunch of stuff moving down underneath the bottom of the water, but it's not like spreading all over the water. It's still relatively close to the ground. That's sort of what a turbidity current is. The deposits are called turbidites. Turbidites are layered and exhibit graded bedding, which is a decrease in sediment grain size from the bottom to the top. So the ocean basin floor features include the abyssal plain, trenches, ridges, and rises. So the ocean basin floor covers about 30% of the Earth's surface, and it begins at the continental rise. And the sedimentation is with passive and turbidity currents. So this contains abyssal plains, deep sea trenches, and seamounts. So you put all those together, you get the ocean basin floor. So the first thing here is the abyssal plain. You can see again on this diagram right here where the abyssal plain is. It's basically just a relatively deep area of the ocean, and it's just very flat. This is the majority of the ocean floor that they say is, quote, unexplored. It's just these very deep areas that are relatively flat. There's really not a lot of contours on the bottom. So yeah, what I was saying, deep, flat, deep ocean floor, depth maybe 2 to 3 miles or more, and it's a thick sediment accumulation over oceanic crust. So, deep sea trenches, the next feature. So occurs at subduction zones where oceanic crust is forced downward into the mantle. So basically this comes back in review to when we did, well actually I think you did it with Miss Stoddard double, maybe, but you guys did plate tectonics. So when you have two plates that are, basically meeting at each other and pushing up against each other, eventually one gives. And when one gives, it basically slides underneath the other like this. And when that does, the two keep pushing together and pushing together and pushing together and pushing together like this, which causes a trench. So it's associated with earthquakes and volcanoes. So on this picture here of the, it more or less highlights the Pacific tectonic plate. So it runs over from where California is, over the San Andreas Fault, up to the Aleutian Trench, down by the Japan Trench, all the way down to the Tonga Trench and the Alpine Fault, and then the East Pacific Rise. That whole area is the Pacific Plate. So the deepest is the Mariana Trench. That is located, if you can see in the picture here, underneath the Japan Trench. That is where James Cameron took that dive in that crazy privately funded submarine, and he went to the bottom of the ocean. I showed you that video, I believe, either last year or a year before. And the longest is the Peru-Chile Trench, which is approximately 5,900 kilometers long. It's pretty long. Okay, next part. Chemical and physical features of seawater and the world ocean. So water molecules stick together with hydrogen bonds. This effect is called cohesion. I might be running over some chemistry stuff if you've taken chemistry yet. In water, hydrogen bonds are formed between hydrogen and oxygen atoms of adjacent molecules. So you can see the hydrogen bond between these water molecules right here. So the states of water. Any substance on Earth can occur in three different states or phases: solid, liquid, or gas. So in this case, condensation is a gas changing to a liquid. Liquid evaporates back into a gas. Freezing turns a liquid to a solid. Solids melt to become liquids. Sublimation is when a solid changes into gas, and a gas becomes solid through frost formation. That should be in review. That's some old stuff, if I recall. So water molecules in a gaseous state move faster than those in a liquid state. Water molecules in a liquid state move faster than those in a solid state. And then, as molecules move faster, they move further apart. So density of water. As water cools, the molecules move closer and the volume decreases. As the volume decreases, the weight stays the same, and thus the water becomes more dense. The colder the water, the more dense. So the colder the water, the more dense. Remember that. Well, then what about ice? Well, ice is a crystalline structure. It's crystals. Molecules are more spread out than when they're in a liquid. So floating ice acts as an insulating blanket that helps keep the water below warm. So when you see a sheet of ice over a pond, the floating ice acts as an insulating blanket and actually keeps the water below warmer. That's actually a benefit when you have a lot of aquatic organisms that otherwise couldn't handle those cold temperatures. So seawater. The characteristics of seawater are due to the nature of pure water, which is a universal solvent, and the solids dissolved in it. It's called the solute. Solids are dissolved in seawater by weathering, hydrothermal vents, and volcanoes. Salt composition. Seawater has a lot of solutes dissolved in it. You can remember, solutes are dissolved material. So 98% of the solutes are made up of 6 different ions. Do you remember what these are? Do you remember this from chemistry? So that's chlorine, sodium, sulfate, magnesium, calcium, and potassium. So sodium chloride, ions make up 85% of these solutes. That's why seawater tastes like table salt. So salinity is the total amount of salt dissolved in the seawater. This can change. It's expressed in parts per thousand, which is the number of grams of salt left behind when 1,000 grams, or in this case, the number of grams of salt left behind when 1,000 milliliters of seawater is evaporated. Such an example is this. 1,000 grams or 1,000 milliliters of seawater is evaporated and 35 grams of salt is left behind. What do you get? What is the salinity? 35 parts per thousand. So the average salinity of the ocean is actually 35 parts per thousand. The hotter weather results in increased rates of evaporation, causing the salinity to be higher. So the Red Sea, the salinity is 40%. Now the Red Sea is much further south, much further towards the equator, so it's warmer. Versus the Baltic Sea, which is 7%. 7 parts per thousand. So it's much further north, it's much colder, there's less evaporation, salinity is lower. So salinity increases when water is removed by either evaporation, freezing, because ice is almost pure water. When water freezes, salt is expelled out. There is no room for salt in the crystal structure of water. Isn't that crazy? So when you have seawater that is so cold, eventually the water molecules push the salt molecules out. So what's left behind is almost pure water. So salinity decreases when water is added from precipitation, such as rain or snow, runoff, or glacier melt. I think we are coming up towards the end for today. So density of seawater not only depends on temperature, it also depends on salinity. The saltier the water, the more dense it is. The colder the water, the more dense it is. Okay, keep that in mind. Ocean temperature varies more than salinity. So density is controlled more by temperature than salinity. So ocean temperature varies more than salinity. So temperature is a bigger deal. Makes more of a difference than salinity does as a whole in the ocean. So reversing thermometers and electronic thermometers, also known as Klein finders, are used to take temperatures at various depths. So the temperature profile, which is basically a graph that shows temperature at different depths. The vertical axis appears upside down. And you can see that there in that diagram. So this is the real-time sea level. We're going to get into that. So that is it for me for the day. I hope you enjoyed the screencast. I hope it kind of shed some light on the quality, sort of the, I guess maybe things that you hadn't really thought about when you look at the ocean and all its capabilities. And I think I'm almost out of time on the screencast, so I will catch you all later. I believe you have some assignments on Google Classroom. Otherwise, I'll see you tomorrow. Have a good one.